All right, we're going to pick up from the idea that we did in 6.2 regular to 6.2a today. And before I actually go too far, I do want to kind of point out in the 6.2 one, I just noticed this just now, I didn't actually answer this part right down here where it says set up the area using two different formulas. Let me just say something to those area concepts that are listed there. One would be that once you got this law of cosines done and you be triggering this law of sines, you do end up with a side angle side connection right there. And one of the formulas you could definitely use would be the side angle side variant, which is that 1/2, and it would be 8 times 9, the two sides, and sine of 123.75. This is the side angle side variant that you could use for that too as well. Now, another variant that you could use to find the area, probably been around nearly as long as the Pythagorean theorem because it was invented by a Greek scholar. It happens to be a side-side-side variant referred to as Huron's formula. Okay? Some people call it Hero's. I think it's Huron's formula is what it is. You might have to look it up. It actually boils down to an idea that it is the area is equivalent to, and the Huron's formula turns out to be the square root, and keep in mind this is like a 3,000-year-old equation. Somebody who came up with this is totally awesome. Is S, now that S doesn't stand for the side length, it stands for the semi-perimeter, and what you do is you take the semi-perimeter and you take it and you subtract off each of the sides from it. It's not a 5, it's an S, minus B, and S minus C. And so the semi-perimeter, let me talk about that part is first. The semi-perimeter is actually taking 1/2 of A plus B plus C. You take all the sides added together and you cut them in half. That's a semi-perimeter. And then you ultimately multiply it in that particular formula. Now, somebody figured that out. Huron did. And he published this a long time ago because ultimately, think back then, what was the only thing you were able to actually measure back in ancient Greece? And the only thing you could really get your hands on would be the actual side lengths of a triangle. And then you could add them up and divide by 2. That's relatively an easy concept. Now, multiplying them would be not too bad either, and estimating their square root would be doable as well too. So think about it in terms of an old sense. Calculators don't exist. I can actually, thrash my abacus enough to figure out this particular kind of question, which is kind of cool in its own right, that even something that's 3 or 1,000 years old could still be useful even in today's law of sines and law of cosines questions. Now, let's get to 6.2a today. 6.2a, couple of review questions because I think both of them are good. Explain when you use the law of cosines. Law of cosines works on SSS and it works on SAS. Those are the two you have to use for law of cosines. Law of sines, on the other hand, works on 3 variants. Those 3 variants are angle, angle, side, which there shouldn't be any issues with. Angle, side, angle, no issues with that kind either. Or big old fat star on SSA, because that one is the one you have to check to decide how many triangles you have, okay? So that is a good way to kind of break down when should you use the law of cosines, when should you use the law of sines, okay? Now, second question that's listed in there, we're going to run into some questions today that might involve using bearings. Bearings were actually derived around people using a compass. And when you use a compass, you can't use east and west, your normal x-axis, as a place for you to take a measurement from. Doesn't make any sense because the magnetic poles of the Earth are in the north and the south. So when we talk about a bearing, we always think about starting on a north or south line. So if I say I want a bearing of south 45 degrees west, I start on the south line and I go 45 degrees to the west-hand direction, and ultimately I would be in quadrant number 3. Okay, now we're going to see some bearings in these next couple of questions, and I want to make sure that none of that actually surprised you. All right, so be aware of that. Now, first question we're going to talk about is going to be about an area question. So remember, we're talking about area of the shaded portion of the circle. Well, I can't even see the shaded part of the circle, but this guy has a radius of 8, so I'm going to put it out here like this, and that would be 8 centimeters. And then it has a central angle size of 135 degrees, something that looks like this. That's 8 there as well, too. And I really think what the question was really asking for is that creates a triangle that goes across like that, and the shaded region was this one over here. It's like I had to take that individual sector and I have to subtract the triangle out of it. Okay, now let's kind of get a game plan for that. If I wanted that shaded region right there, I would take the area of the sector and I would subtract the area of the triangle from it, and I would get the area of the shaded that's listed right there. Now let's put this formula together. A sector is calculated by doing the central angle 135 divided by 360, because it's only a portion of a circle, pi r squared. All right, that seems like a pretty straightforward deal here. I'm going to change even the r on this one to 8, because I know that it's 8 squared, minus the area of the triangle. Now that triangle happens to be pretty cool. It's a side angle side triangle, which means I could use the side angle side area formula on it, which is 1/2 the adjacent, the base, sine the angle. So in this case, it would be 8 times 8 divided, or times sine of 135. And that's that one that was up above there, above Huron's formula. Now, ultimately, plug and chug. Let's see whether or not we can get an answer for this bad boy. And the key here is to just be smart about how you use your calculator and calculate things the correct way. 135 divided by 360. And what you're going to get good at as you go along through your math career is about holding on to answers. This is going to be multiplied by 64 pi. And that answer right there is one that I would say, okay, I know that that's what this half is. Maybe writing it down on your on your paper is a good idea to help keep track of what's going on. That's 75 point, basically 4. Okay, I'm not going to use that number. It's just to help me keep track of where that came from. And then I would do the other side of the question, which is 0.5 times 64 times sine of 135. I'm just combining some things together. That's the other side, 2.82, triangles using up so much. And then I'd ultimately want to, maybe I'll put that down, 2.82. And I'd want to subtract those two values. And the cool thing about your calculators is it allows you to come back to old answers and then subtract them without really truncating them or anything. And now I could get an answer of 72.57. 72.57 centimeters squared. All right? Good plan, right there. Good plans lead to good answers. Yeah, that's right, baby. Woohoo! I'm a geometry genius. All right, let's go to number 2. A couple of other like guided kind of questions that we're going to see here. You are on a fishing boat. Now, this is where we all need to be because COVID is keeping us at home. We would much rather be on a fishing boat. Now, that fishing boat leaves the pier and it heads due west. Now, the best thing you can get right here is a really solid picture. Here's your pier, and you're going to head due west. Woohoo! We're headed out to sea. Okay? You travel for 20 miles along this actual trek, and you're like having a great day. Maybe you caught some stuff. Maybe you got some tuna. All right? And then you hear a reported warning that there's some rough seas up here to the north. So you decide to turn. Now, here's where the most important part of the story happens to place. The captain, Captain G. Okay? My favorite letter is the C. Get it? Never mind. He turns the boat and follows at a bearing. Now, where was this bearing actually taken? Well, that was me sitting at this spot where I took the bearing. This is where I looked at the compass and I decided to turn the boat. It is not over here at the pier. The compass is on the boat when I decided to turn, and that is south 32 degrees to the west. So ultimately, I decided to turn the boat in this direction at an angle right here of 32 degrees from the south line. Okay, this is where you've seen people, they roll out the map, they put the compass down, they decide on taking a bearing. Okay, now ultimately we follow that particular path for 11 miles, and somebody at the pier wants to get a hold of us and figure out where we're at. At this time, how far are you away from the pier? Line being drawn all the way out there, and you need to find that X value right there. Now, here's the deal. What are you staring at in terms of side angle side, 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 whatever it is? Well, it can't be side, side, side. You're looking for a side. This is a side, this is a side, and that right there is an angle that's going on right there. You're dealing with a side angle side, so this must be a combination of the law of cosines. And you've got to find that side length over there. That would be x squared is equal to 20 squared plus 11 squared minus 2 times 20 times 11. Cosine of, now I'm pausing right here because I'm like, uh-oh, is it 32 degrees? No way. The whole entire angle is obtuse that's inside here. So technically it's 90 plus 32 degrees based on that bearing, or 122 degree bearing. Okay, this is probably why you've heard in movies or something like that, we're going to take a bearing of 122. They're trying to get you to think about the ideas that bearings can be simplified into a 360 degree circle in that concept, which is an off-topic concept, and now I can put 122 in there. Okay, let's see if we can triangulate our position of where it's going to be at. That's a plug and chug side angle side. Let's see what kind of number we can get out of that. 20 squared plus 11 squared, awesome, minus, now if you're getting pretty decent at doing the law of cosines, you're probably realizing you could probably do all this at the same time. Just be careful if you do so. Make sure that you got things that are in parentheses and you're watching out for your PEMDAS stuff. And cosine of 122 degrees, close it twice. Cha-ching, bada bing, you're not 900 miles away from the shore. You have to take the square root of that answer. Don't forget that. You are 30 miles from the actual shore. 30.03 miles away. Okay? In general, this is real life kind of question. If you don't have GPS, you better know how to find your bearings. You like that? Get your bearings. Never mind. All right, now, here's a question. Something's happening out here at the ship boat. G catches a marlin, but it stabs the boat with its sword nose, and it starts to go down like the Titanic. I need to radio back to the pier, somebody to come help me. I know that I'm 30 miles away, but that could be 30 miles away in any direction around the pier. You could die at sea. What bearing does the person at the pier need to take to actually come and find you at that spot? Well, the only angle that's inside the triangle is this one right here. That's not technically a bearing, but it could help. How would we find that particular spot? Now, you did end up finding the side that's across, which is your 30.03 miles that's listed right there. And you do have the angle that's across from it, so I think we've got enough for a law of sines here. 30.03 miles divided by sine of 122 degrees is going to equal this one, which is 11 divided by sine of angle help, angle H, let's call it, okay? Or angle P. Ooh, we should call P for pier. That makes more sense, okay? Angle P. I like to have fun with these problems. Now let's see what the calculator says on this. We can triangulate our picture, our place again. 11 times the sine of 122, and that answer divided by, I'm going to actually use this one right here to make sure I got the right number. And then I'm going to take the inverse sine of that answer, and I would generate Ooh, that turned out to be in radians. See how I knew that that was a bad answer? Yuck. I bet you I need to go back and figure out that question all over again because I don't think 30 is right. Dang it! Now I gotta do the problems all over again. Pause. All right, I went back and I recalculated that question, and this is why I would die at sea. It's not 30 miles. Dang it. I had my stuff in radians. Now, I did that on purpose. No, I didn't. Okay? To actually show you, it's really super easy to miss the mode on your calculator. This answer should have been 27. Let's see what I got there. 27.46 is what it should have been. So 27.46 miles is what's going on there. Sorry about that, guys. Which would change this question down here. And I'm going to put that that's 27.46. And now I can start recalculating my question again. Sorry about that. Go back and fix it. Now, let's see what we got here. We've got 27.46. That's this answer. And no, I don't want to do that yet. I want to do 11 times sine of 122. Okay, that part's working good now. Got that. Time, divided by the 27.46. Boy, I'm getting all off here. That's okay. It happens. Take the inverse sine of that answer. Angle for P, 19.86 degrees. Okay? Now, be careful. This answer right here, that's not the bearing. See how the question said it wanted the bearing? You just found this angle right here. But as I said, bearings are always measured from north and south. So what's the south bearing to get there? That is a southwest bearing, and that southwest bearing would be the complement to 19.86. So I would go 90 minus this particular answer, and I would get a bearing of 70.14. 70.14 degrees southwest is which direction we would go, okay? Now, go back, make sure that you verified all my answers are looking pretty good. So far, I think I did okay. If I made a mistake, come by and make fun of me, okay? That makes you feel better. Number 3. Okay, let's see if I can do this one without a mistake. Number 3, it says 2 tracking stations are on the equator and they're 236 miles apart. Okay, now these tracking stations, these are real concepts. We're going to call this T and this one L, something like that. And they happen to be right on the equator, and they are 236 miles apart. Okay, now that's really helpful. I got myself a picture that's going on. A weather balloon located at a bearing of this from the western station. Okay, so this is the western station. So there's a balloon that he sees at a 38 degrees to the east. So he's like, hey, I'm going to look over here. This is a 38-degree angle from the north to the east. And he sees the balloon. I'll try and draw a balloon. Balloon. And it's got a little basket. Okay? Now, the other sees it from a bearing of to the west. It sees the balloon like this. And that angle is a 16-degree angle to the west. So see how the bearings are taken at the actual stations themselves. The question is, how far is the balloon away from the eastern station? So how far is this distance in this spot? Now the funny part is you don't actually have any angles that are in the triangle itself. You're like, dude, I need a triangle. I need an angle inside here. And if I found this individual angle, it would be the complement to the 38 degree. Now, it's very common that bearings will force you to find complements. So if I subtract 38 from 90 on that one, that's a 52 degree angle. 16 from 90 is going to be 74 degrees. I think that sounds right. That's 74, 6 is 80. Well, that's 90. All right. Looking good. Now I got myself a really true triangle that's going on right here. And ultimately, you're kind of like, I want to use this combination, but I don't have a law of sines yet until I have this angle up here in the top corner. And you can find it relatively easy by doing a triangle subtraction deal. So I've got 180 minus 52 minus the 74, and I would end up with an angle of 54 degrees up here in the top. And now I have a direct across combination. Law of sines, baby. That's where we're going. I don't know why this is even in the law of cosines section. It's really a law of sines deal. I can set it up as 236 divided by 54 degrees, sine of 54, is going to equal x over the angle that it's across from, which is sine of 52 degrees. Okay, cross multiply and solve. Let's see what we get. 236 times sine of 52. Woo-hoo. And then divide this answer by the sine of 54. And I'm praying that that's still in degrees. Oh, it is. Okay, don't want to make that mistake again. X is 229 point, how many miles was that? 0.9 miles. And you know where that weather balloon is at. That weather balloon could have been seen by somebody, and maybe it was a UFO. You just never know. Okay? All right, I don't know why that question's really in there. It's not really a law of cosines. It's really a law of sines. And I don't see any other way I could think about doing that one. Sounds good. Just make sure that you draw your bearings from the locations of where the bearings are being taken. That's the most important part to get a really solid picture in any one of these guided real-life kind of questions. All right? Pay attention to what's going on and solve your word problems up. When you struggle with something, circle it, find it, ask your teachers. They are dying to do problems on the board. And if you're not asking questions, you're not doing your part as a student. Get her done!